Audio Jungle. Audio Jungle.
Rocket equation now. Rocket equation. Rocket equation for a series multi-stage rocket. Now so here one big diagram I will draw, so it will be very easy for you to understand this. Okay, so okay, you just say this is but two stage only. All right. Payload, you just say as per numbering, because if you solve, then first one, this is first stage you can say, okay, and this is what second stage. Let me correct this. This numbering is just opposite, because that removal, once first stage will burn, then you will go for the second stage, so that this numbering I have given wrongly. So let me correct this. That random numbering I had given, so there should not be any kind of confusion here, because first stage will be downside, because first once burning will start, then first stage will burn and it will be removed, then it will go to second stage, then it will go to third stage, like that. Okay, so this is what first, second and third. This is what payload. All right. Anyway, so now how to write the equation for the single this series multi-stage rocket system. So the standard formula you know, and the standard formula is what? For the change in velocity, it is delta v is equal to v equivalent ln 1 upon mr. This is the formula we know, or I had given this is also ISPG ln 1 upon mr. This formula in last section, last lecture you had seen, right? Now, so because this is for single stage, or this is for single stage. Now if you go for multi-stage, So for multi-stage, you will have a delta V, and this delta V will be the summation for all stages. I is equal to 1 means started from single stage to n number of stages. Capital N is the n number of stages, and this delta V I means for all stages you need to calculate this change in velocity and algebraic sum. Summation means here this symbol it is used, so this is what algebraic sum. So you add all and then final you will get for multi-stage. Yes or no? Final you will get multi-stage. So this is the formula, means for each stage you will calculate delta V. If it is n number of stages, max to max 3, 4, whatever the number of stages you have. If it is 3 stages we have, till third stage you calculate delta V1, delta V2, delta V3, add all. It will be the calculation for the third stage. I can write here also third stage. So if I say what is for third stage, so this third stage value, it is nothing but delta V is equal to, for the first stage delta V1, second stage delta V2, third stage delta V3. Alright, the same thing, the same formula we can write in our standard format. So for our standard format, this formula will be, I can write delta V is equal to, I am talking about multi-stage and in bracket n number of stage, multi-stage rocket. I am talking about n number of stages, right? So what will be delta V? Delta V is nothing but I is equal to 1 to n, and this is nothing but delta Vi. This also you can write summation I is equal to 1 to n. What is the formula? It is V effective of I ln 1 upon mr is mf by m naught. So m naught will come in numerator, check the formula, and m naught by mf I. This if you write in terms of ISP, okay, and this is also you can write G will be constant for all, but ISP will not be constant, because for each step stage ISP may change, because suppose some stage have a solid, some stage have a liquid, then obviously ISP will be changed. So ISP you have to calculate for that particular stage, ISP I, okay, ln 1 upon mr I. It's your choice. If you want to write m naught by mf, you can write. So here in all format I have written, so there should not be any kind of confusion. Done. Now this delta V also you can write. So whatever I am writing here, I am not deriving anything. Whatever result we got in last class, the same result we are manipulating for the multi-stage system. Okay. Now this delta V is equal to I is equal to 1 to n number of stages. It will be delta Vi is equal to summation I is equal to 1 to n V effective of I ln. If you remember, this is also the formula I had given. In many format I had given formula, okay, lambda I plus delta I, Okay, lambda I plus delta I, or the same thing you can write, it's your choice, you can write the same thing. If ISP they have given the same formula, you can write I is equal to 1 to n delta Vi is equal to I1 to n number of stage. ISP G you can take outside because G will be constant. ISP I1 ln 1 upon lambda I plus delta I. Lambda I and delta I, if you remember, it was the fraction, payload fraction and structural fraction. If you remember, it was payload fraction and structural fraction, right? Or the same formula I had given in one more format, and it was in terms of the structural. This is the first. You just keep this in a box, so it will be easy to remember. The both are the same formula, okay, and put in box for the series multi-staging rocket system. And we will solve one problem, so it will be very easy to you. It's very simple only, okay, don't think it's difficult, it's very simple. Now, so this format is nothing but I can write here, this is the delta V is nothing but I is equal to 1 to n number of rocket. It is V equivalent of ln 1 upon MRI. This formula also you can write I to 1 n ISP ln 1 upon MRI is equal to, if you remember, the formula was I is equal to 1 to n V equivalent of I, and this is what ln 1 plus lambda I divided by epsilon I plus lambda I. So this is the final formula. This is the final formula. Okay. This, in short, this formula is very important because for multi-staging they will use this formula most of time. So again I will write this formula. Please check it. One plus lambda I, which is the propellant fraction, epsilon I, which is the structural coefficient, epsilon I plus lambda I, again propellant fraction, okay, or I1 to n ln, sorry, it's ISP, na? So just remember this formula, it's very important, okay? This will help so much. ISP I ln 1 plus lambda I divided by epsilon I plus lambda I. Okay, this is very important for serial multi-staging rocket system. done. And this is very simple only how to remember, because we already have derived, so for multi-staging we can write this. Or one more thing, now key points or note you can write here. What is the note? Note when the effective effective exhaust velocity V equivalent and mass ratio are the same. Listen carefully, are the same. This is very important note, okay, for all stages. Okay, what they said, if effective exhaust velocity means V equivalent and the mass ratio, if these are same values for all the stages, and now we are having n number stages, so for n number of stages, what will be delta V? So we are having n number of stages, so n, and for all stages velocity is what? Same, V equivalent into ln 1 upon, so V equivalent into ln 1 by mr, this is what? This is for single stage, and for all stages this effective exhaust velocity and mr, mass ratio is the mr, if it is same for all stages, so n number of stages we have, so multiply with that, that's all. So ISP G ln 1 by mr and just multiplied by n number of stages. Done. This is very important, okay, you need to write somewhere, because most of GATE question they will ask based on this. They will say for all stages these values or ISP or effective exhaust velocities are same, okay. So remember this. This is the very important, okay. And it happens, when this happens, then what will happen? Then the overall payload ratio, okay, lambda, will be equal to product of all payloads. This is also very important. If this happens, okay, so this is the point 1, this is the point 1, and what is the second point? Second point will be, if this happens, then you need to write the total payload, the overall payload ratio. I'm talking overall payload ratio, not payload mass. I'm not talking payload mass, I'm talking about payload ratio, okay. So the payload ratio will be lambda naught, and this value will be n times lambda of I, okay, equal to the product of all payload, or you can write in this format, 1 to n, and this is nothing but lambda I. So this thing will happen when the effective exhaust velocity and mass ratios are same, then delta will be this, and your overall payload ratio, okay, I can write here overall payload ratio, which is lambda naught, is equal to is equal to the product of all payloads, product of all payloads. Here this one I just need to correct this symbol. This is the algebraic sum, but what is the product notation that I will draw? This is the algebraic sum, okay, but it is not algebraic sum, it is the product of all payloads. So product, how to show that product will be this. This is the symbol for the products. Okay, I can say this some symbol will be used for product. I is equal to 1 to n into lambda I. Okay, so what is the lambda naught? Lambda naught is nothing but products of this symbol is what products. Okay, I is equal to 1 to n, and this is lambda I. Or in the another way you can say overall payloads will be equal to the product of all payloads. So suppose n number of values we are talking, so it is lambda 1, lambda 2, lambda 3, lambda 1, lambda 2, lambda 3. Okay, for n is equal to 3 till third stage, this will be the payload ratio. Okay, you remember this is the algebraic sum. Okay, algebraic sum, and this symbol basically use product. Okay, so remember this. Anyway, all right, so this is what the series multi-stage. Now we'll go for the parallel. So how to get that equation for the parallel? So rocket equation 0.2. Rocket equation for a parallel multi-stage rocket. Okay, I have drawn the diagram. Again I will draw here for your understanding how parallel staging will be. So this is what parallel staging. Okay, parallel multi-staging. So I can say for k number of stages, for k number of stages, what will be the total thrust, because each stage will give the thrust and obviously it is parallel, so thrust will be added. Sorry, total thrust as the sum of all engines, sum of all engines. Now check here, you will get thrust, here also you will get thrust, here you will get thrust, but in this series this thrust will be here only, no? Check, the thrust you will get only here because it is the single stage. Anyway, so listen carefully, it's very simple. All right, so what will be the total thrust? So total thrust will be the summation, how many engines, suppose number of K engines we have, number of K rockets we have, then it is nothing but the total mass, because every one having a mass flow rate, so m dot p total, okay, m dot p total, or better you will write m dot p I, no? I in the sense is total number, because we are writing I is equal to 1 to K, so it is m dot p I into V effective I. All right, what will be the total mass? Total mass flow rate. What will be the total mass flow rate? So obviously total mass flow rate m dot p total, it will be summation of, it will be summation I is equal to 1 to K m dot pi. If it is 3, then m dot p1, m dot plus m dot p2 plus m dot p3. We have a 3 engines. Hope you understood. This is very simple only. Okay, so it's not difficult, it's very easy. The point is understanding. If you understood this, then it will be very easy for you. Directly don't mark up formula, just read this headings, lines here, and automatically you will understand by the diagram. Because see, if you check here, you will get m dot p1, you can say, here you will get m dot p2, here you will get m dot p3. So what will be the total? Total will be summation, so that I have written only m dot p V effective for this rocket, m dot p1 into V effective 1 for this rocket, m dot p2 plus m dot p2 into V effective 2 for this middle rocket, and this third rocket m dot p3 into V effective 3. If you add all, then you will get this, simple only. Okay, so this is the thrust and this is the mass flow rate. Okay, it's very simple. All right, so if you calculate the total thrust, because it is not same for all engine, because middle one engine suppose is what more stronger, this middle engine is what suppose more stronger, and these two are the supplements. Okay, so obviously the thrust will not get everywhere same. Okay, so that time what you will write, average thrust, you will say average thrust. Okay, so what will be the thrust force? So this thrust force we will get average, and average in the sense what? Average will be the velocity. So this thrust, total thrust will be m dot p total into V effective exhaust velocity, and this value will be average. Why I am saying average? Hope you understood, because everywhere we are not getting the same exhaust speed, because strength of each rockets are not same. Middle one may be more stronger, and this middle one is what going for the mission, and these two are only just for supporting during the lift off condition, and then these two supporter will be removed. Okay, so that means all three are not having the same exhaust speed, so you will get average exhaust speed. How to get? We can write here, V effective average or V equivalent average is the average exhaust speed or velocity, and how to get this, and it is given by check this formula. If sometimes required you can calculate, otherwise most of time this value will be given to you, so nothing to worry. How to get average? So average will be, check, total thrust divided by total mass flow rate of the propellant, and this is equal to, you have seen what is the total thrust. See this value, this is the total thrust and this is the total mass flow rate. You write here. So this is what, I is equal to 1 to k number of engines, m dot p I into V effective I divided by what is the total mass flow rate of the propellant. It is I is equal to 1 k engines, no? I is equal to 1 to number of k engines, m dot p of I. This is the average velocity. Till now in your gate they have not asked average velocity. Max to max they will ask you what is the total thrust, that's all. But if they will ask, you can calculate by this way. Now, so what is the final change in velocity, because that is your ultimate motive, right? So I will write then change in velocity for rocket parallel multi-stage rocket. No, for parallel multi-stage rocket. So because that is your ultimate goal, you for series multi-staging also you did same. Okay, change in velocities. What is change in velocity? It is delta V. Now what will be the delta V? So what the delta V will be the V effective exhaust velocity into, and this effective exhaust velocity will be what? Average. Okay, and then ln m naught by mf. That's all. Because delta V is your ultimate goal. Okay, so for delta V for parallel multi-staging is V effective average ln m naught by mf, because you are calculating delta V, so this is the standard formula. Instead of effective exhaust velocity you need to write average effective exhaust velocity. And how to get average effective exhaust velocity? This is the formula for the k number of engines. Okay, and this is for the parallel multi-staging, and this is the change in velocity for the this formula. Basically this is the change in velocity for the series multi-staging rocket. All done. So this is the theory behind series multi-staging rocket system and parallel multi-staging rocket system. All right. So this is for the series multi-staging rocket. This is the problem number 1. Problem 1. Okay. A three stages rocket is designed to place a small satellite satellite into the low earth orbit. You might heard this word. It is called LEO. Okay. Having a payload weight of 200 kg. Data for rocket is given in table below. Calculate increase calculate the increase in its speed, which is delta v. So they are asking delta v. How many stages we have? 3 stages. Check this table, all the data they have given to us. Okay. Stage number ISP in second. Total mass in kg. Propellant mass. Propellant mass also in kg. Okay. Propellant mass. Now 1, 2, 3. 230, 250, 250. 14,000, 4,500, 1,000. Propellant mass 12,800, 3,700 and 700. Okay. Now this is the data for all the stages. Now we'll go for the solution. So little bit fast I will go because it will take so much time. So we need to write for for 3 stages. What is the hence? What is capital N for series multistaging? It is 3. How you would know it is the multistaging system? How you would know this is the multistaging? It is series multistaging rocket system. So see, in this case, they have given for all the stages, they have given ISP. If you check the total mass, okay, that for all stages they have given, and propellant for all stages they have given here. So in the question are 3 stages. In a question of 3 stages, rocket is designed to place a small satellite into the low LU having a payload weight of 200 kg. Data for rocket is given table below. Calculate the increase in speed delta V. So in this way the problem they have given, and for all stages they have given the value. Okay, so you need to consider this is what the series multi-staging rocket. How that data will be given for parallel. I will solve one parallel rocket, multi-staging rocket. Then with the given data you can understand this is what the series and this is for the parallel. All right, so first we'll solve this, and parallel also will solve. Then I will show you the comparison, and then in that way you can understand, because they have not used that word, but with the given data only you can understand, okay, this is for the parallel and this is for the series multi-staging. All right, now so this problem I am going to solve. This is for the series multi-staging rocket, and I will write here also better. Series multi-stage rocket. Here for series 3 stages we have, hence capital N is what, 3. And now if you want to calculate the change in velocity for this multi-staging rocket system, so I had given formula delta V is equal to, it is I is equal to 1 and N is what, 3, and this is what delta Vi. So need to calculate delta V1, need to calculate delta V2 for second stage, need to calculate delta V3 for third stage, and we'll calculate this value easily. Okay, now the same formula what we can write delta V. I just broke this formula so you can get this I1, and this is what N, which is nothing but 3, and this value is what delta Vi. This is also because ISP they have given to us, so ISP will use, and N is equal to 3, and this is the ISP I, and we know ln m naught by mf, ln m naught by mf, and separately they have given the propellant mass also. So what is the mf? Mf, you remember previous lectures, it is m naught minus mp. This is the mf. Okay, so this formula we need to check. This is already explained. Okay, this is not new for you. So I'm going to write this formula, and for each stage you need to calculate this delta V, which is because ISP they have given, so we need to write this formula in terms of ISP, and here it is given 3, and this is ISP for each staging I, and we have ln m naught by mf. I told you m naught, which is the mass, total mass before operation, and mf is the mass after the operation when propellant is what completely consumed. So mf, that formula if you check in my previous lecture, it is given derived m naught minus mp. This is the mf value. Okay, I. All right, done. Now how to break this that 3 stages we have, and these 3 stages we need to break in stage 1, 2, 3. In that way we need to take. So full scale diagram I will show you, and then I will show you like, okay, if first stage will be removed, then what will happen? If second stage will be removed, then what will be happen? Based on that diagram only you need to perform. Then it will be very easy for you. Okay. So I can say this is the first stage. Okay, in this first stage, this is the say mass of propellant. I can say this is first stage, so hence this is the mass of propellant 1, MP1, and this is the structural mass MS1. Okay, and this total mass will be M01. Now second stage, because three masses system I to explain you what are that: initial mass which is M0, propellant mass which is MP, MS which is the structural mass. Okay, so MS1, MP1 and M01. Hope this one is clear. Now we'll go for the second stage. For this second stage, this is the MP, because second stage, so mass of propellant for second stage, and MS2 which is the structural mass for the second stage, and obviously M02 also you need to draw. I am considering this is containing this full rocket. When operation is what going to start, then this is the mass distribution for the rocket. Okay, all right. Now we'll go for the third one, which is nothing but here. So this is the third stage. Okay, and here we can say this is MP3 and this is structural mass MS3. Okay, and finally this is the payload. Finally this is the payload, and this payload is nothing but ML. This is the full rocket. Okay, this is the full rocket. This is the first stage of rocket. This is the second stage, and this is the third stage, and this is the payload. All right. So this is the first. What will happen when the first stage is what removed? Okay, so when the first stage will be removed, then you will have from here this part you may have only, and this will be the M02 now. This is the mass of propellant for second stage. This is the structural mass MS2, and obviously third stage will be there because first stage is what only removed. So where is the third stage? This is the third stage. MP3, MS3, and obviously payload will be there. There is no question about it. Payload will be there. ML. Now if second stage will be removed, then what will happen? So second stage will be removed, then you will have only this part. Third stage, in this third stage you will have propellant of third stage MP3, structural mass of third stage MS3, and you will have payload. Okay, So based on these two diagrams, we need to solve the problems. During the operation of the rocket, this is the progress. Progress block diagram of rocket one by one. It will start from here, then it will go to here, and then it will go to here. And after third stage, definitely means first it will be launched, and then that third part will be removed. Yes or no? Done. Now so we'll go for the calculation, and we are going to talk about the first stage. We are going to talk about the first stage. So let me write here first stage. First stage. So since the payload is carrying at top third stage into orbit, okay, the total mass of first stage is m01 as per diagram. Now everything will be based on diagram: m0, mp1, ms1, mp2, ms2, mp3, ms3, ml. Everything you should know. Based on this diagram only, I am just going to write and solve the numerical. Okay, so this is m02, and here this is what, m03. I have not written m03. Okay, anyway. So what is the total mass m01 for the first stage? M01, it will be m total mass of mt1 plus mt2 plus mt3 plus ml. This is what? This is the total mass. This is the total mass. Check what is the m01, what is the mt1. If you check here, total mass, I'm just going to talk about total mass. Check the table. Total mass is this one, 14,000, 4,500 and 1,000, and payload mass is here given, it is 200 kg. So we'll add all. Okay, so we need to go very fast for the calculation. We should not waste our time in calculation, because important is what? Theory here. Once you know the theory, then it will be very easy for you. mt3 is 1000 plus ml I have 200. What is the m01? Where is my calculator? It is 1400 sorry, plus 4500 plus 1000 plus 200. It is 19,700. This is the value. Okay. In the formula, if you check, what is the formula? m0 minus mp. If I'm talking for first stage, right? So I can say, what is the m01 minus mp1? So it is 9,000. Oh, 19,700 minus what is the mp1? Check. In first stage, what is the mass of the propellant? Here, mass of the propellant, see, first stage, it is 12,800. It is 12,800. What value? Minus 12,800. I am getting 6,900. This is the m01 minus mp1. Okay, what is the delta v1 now? Delta v1 is nothing but is p1 g ln m01 minus M01 minus MP1. ISP1, if you check, they have given ISP1. This is 230. This is 230. So 230, okay. And G you can take 9.8. ln M01 you had seen it is 19,700. M01 minus MP1 you have calculated 6,900 watt. In my calculator I am writing. So if you do this calculation, you will get delta V1. I am getting approximate this value. What is the just hold on. So this is nothing but 230 into 9.8 into 9.8 into 1.049. I am getting 2255. So this is nothing but 2364 approximate meter per second. This is the delta V1. All right, now we'll go for the second stage. In second stage, as the propellant of the first stage is burned off, and once it is burned off, then first stage will be removed. This is what the second stage, yes or no? This part is what, first part is what burned off and it is removed now. You know the operation, many times you have seen on TV, that rocket operation, space mission you have seen. So first rocket is what, first stage is what burned, that propellant is what burned out, then it is removed, then only second stage you may have. Then second stage is what, that propellant is what burned out, then it will be removed, then you will have a third stage. Like that you have seen, right? That mission you have, the latest mission, Chandrayaan mission you have seen, you heard that actually, no? So you just think in that way, and based on that diagram I have drawn here. Okay, now, so second stage, as the propellant of the first stage is burned off during powered ascents, okay, so the near empty tank and structural of the first stage are dropped off, and it is removed to reduce the weight of the vehicle to achieve orbital velocity. So a smaller amount of propellant is retained in the second and third stages tank. Now I will calculate what is the M02 then. So what is the total mass for the second stage? Total mass for the second stage, it will be M02. What will be M02 then? Because MT1, that is total mass for the stage 1, will be removed now completely. Now you will have only second stage MT22, then it is MT3, total mass of stage 3, and then payload it will be carrying, right? So again we'll go fast. What is the total mass for the stage 2? Check here, it is the total mass for the stage 2 4500, and for the third stage it is 1000, right? So please write this value. So second stage is 4500 plus third stage it is 1000 plus payload mass will be same for this, so it is 200. If you add this, so I'm getting 4500, 5500, then plus 200, then 5700. Now again you will calculate, it is called MF, na? MF2. Let me write here also. Here, this is MF2 actually. This is called MF1, final mass of 1. So M01 minus MP1. Similarly, MF2 if you write, then M02 minus MP2. How you will have, how much? It is 5,700 minus, if you check the propellant mass for the second stage here. So what is the value propellant mass? It is 3,700. It is 3,700. So you will calculate this value, you will have 2,000. Okay. Now we'll calculate what is the delta V2 here. Again we'll do the same thing. So it is nothing but G into ISP2, okay, and ln M02 minus MP2. Okay. If you write all the value, all the data here, G is nothing but 9.8. What is the ISP2? Here it is given in the problem. ISP2, that is specific impulse for second stage, it is 250, right? It is 250. M02 you had calculated 5,700 divided by this value will be 2,000. If you do this, then delta V2 you will get. Right. Now we'll go for the third stage. So I'm sure what diagram I had drawn for all the three stages. With that diagram you can solve that this problem will be easy for you. So focus on that diagram only, that's all. So third stage will go. So in the third stage, obviously second stage will be dropped off now. So what will be the total mass for the third stage? Total mass, it will be M03. So second stage also dropped off. So MT2 will be removed now. MT1, MT2 both removed. Now you will have MT3 plus mass of the payload only. What is the total mass? If you check total mass, if I remember, it is 1000 I think, plus mass of the payload is 1200 kg. What is the MF3 final mass for the stage 3? MF3, it is nothing but M03 minus mass of the propellant you need to remove. So it is 1200 kg minus, what is the mass of the propellant? I think it was 700. Let me check. It is the 700, right? It is the 700. So how much will get? 500 kg. Okay, 500 kg. Now what is the delta V3? Delta V3 is nothing but again G into ISP3 ln M03 minus MP3. If keep all data, so 9.8 into ISP is 250. Okay, ln, what is the value of M03? Just now you have calculated 1200 by 500. If you calculate this, so 2144 meter per second. This is the delta V3. And if you check, this problem was little bit lengthier. Why? Because in this case for each stages the ISP was different, no? And for that reason only, even the mass ratio if you check, it was different. So for that reason only The otherwise in gate problem they will give very simplest problem. Okay, so total incremental velocity it will be delta V and approximate to 7075 meter per second, right? This is the value. Done. So one more problem need to solve, and it will be for the parallel multi-staging rocket system. So problem 2. Parallel multi-staging rocket so if you check this problem, they have given the statement for this problem, and at the same time they have given the table. So I'm just going to write the table value. So from here you can start the problem. Okay, in the problem what they have mentioned, you just listen. The shown one figure it is given. The shown figure illustrates European rocket Ariane 5. This is the rocket engine used to deliver payload into the geostationary transfer orbit. Okay, or it is GTO, which is called geostationary transfer orbit, or low Earth orbit (LEO), initially at liftoff of an Ariane 5 launch vehicle, 2 P230 solid propellant boosters plus the main Vulcan engine. Vulcan engine means main engine. Okay, so by the statement only you can understand here clearly what they mention. Initially at liftoff of an Ariane 5 launch vehicle. This Ariane 5 what I am talking, it is the European launch vehicle. Okay, just like we have launch vehicle MK2, MK3, no? So launch vehicle 2 TWO, I am saying TWO 2 P230 solid propellant boosters plus the main Vulcan engine are ignited. So I will draw the diagram. By the diagram only you can easily understand. They said this is the main engine, this is the main engine here, this is the main engine, and this main engine with 2 P230 solid propellant boosters. Okay, so this booster will come alongside, this booster will come alongside, this is the one booster, and this booster will come this side. So this is what parallel multi-staging. So that's the reason I told you this is what Vulcan engine, I must say Vulcan engine. Vulcan engine means main engine, and this is what booster. Name also they have given P230. This is the booster name. Just like a main engine have a name Ariane 5. launch vehicle. This is also booster. Done. So they are asking the two different component of launch vehicle have the following characteristics. The table they have given to us. Okay. It will hardly take 2 minutes. So better I will write numerical, so it will be better understanding for everybody. The shown figure illustrate European rocket Ariane 5 used to deliver payload into geostationary transfer orbits GTO or it is LEO. Initially at just for the aircraft it is take off, so for the rocket it is lift off. What will be used? Of an Ariane 5 launch vehicle 2P230. This is the booster's name. Okay, solid propellant boosters plus the main engine. Main engine are ignited. Two different components of the launch vehicle have the following characteristics. Now check the table. This is the diagram. We have a table and this table you need to use. We can start from the table itself, but I just, because we are solving only two numerical, one for series multi-staging and one for parallel, so I just wanted to write the numerical also completely, so that anytime if you see this problem then easily you can understand. This table value they have given to us. They said engine types. This is what Vulcan or main engine, MAN, main engine. Okay, and this is the booster. What is the booster name? P230. How many boosters we have? Two boosters. So based on that you need to take care once you solve the problems. So engine type you are going to write. So this is what in this engine type we have two types, and what are that? Liquid propellant engine So your main engine is what? Liquid propellant, and this one is booster is solid propellant. And this usually happens this, okay, main engine is liquid propellant and rest booster, because the booster easily it will removed. Once it is lift off, then booster will be removed and this liquid propellant engine will carry that payload to the orbits. Okay, this happens actually, no? So now you will write the value for thrust and you will write the value for specific impulse. For liquid propellant, what is the thrust? And this thrust is what in kilonewton, remember. Okay, and specific impulse will be in second. This unit is what important. What is the liquid propellant thrust? We are getting it is 1114. For solid propellant, we are getting 6470. Okay, and specific impulse we are getting 430, and this one, see that liquid propellant I had given the advantage and disadvantage. That time I told you for liquid propellant engine ISP is what more, and check the ISP 430 and solid we have 275. Now this is the table. For this table what we need to calculate? We need to write calculate number 1. What is the number 1? Listen carefully. Effective velocity for each engine. Number 2, exhaust mass flow rate. Number 3, average effective exhaust velocity. Number 4, average specific impulse. Right, we'll go for the solution immediately. So solution for this problem, hope this one is very clear to you. Now problem is what very clear to you. What we are going to do first, because it is now by the problem only I explain you, and I have drawn the diagram also for this. Now it is very clear, this is the parallel multistaging. Once I had solved problem number 1, and I told you that time multistaging, series multistaging and parallel multistaging, how to recognize. So sometimes in problem they will mention, sometimes they will give the diagram with the data you can understand, and most of time in problem itself they will mention, like here they have mentioned what they have said, one main engine and 2 boosters are used for during the lift off condition. Simple, it means it is the parallel multistaging. Alright, so that's the reason I told you, just wait and see, you will understand once we'll solve both numerical, series and parallel. It will be very clear in your mind, like okay, this is series multistaging rocket system and this is the parallel multistaging rocket system. Hope this one is clear, right? Now we'll go for the calculation. So in the problem itself it is described that we are employing solid propellant engines and liquid propellant engines, and the propulsion system here resembles parallel staging, because with the main engine 2 boosters we are using. Okay, now first we'll calculate effective exhaust velocity. Number 1, effective exhaust velocity. Effective exhaust velocity. So how to check the methods I have given in parallel multistaging, how to get this effective exhaust velocity. So effective exhaust velocity, we know the formula, it is G into ISP. Okay, so for main engine we calculate For main engine we can get this effective exhaust velocity. So here we will have a G into ISP. G is nothing but 9.81 into, for the main engine, which is the Vulcan engine, called Vulcan engine. What is the ISP they have given? It is, I think, 430. 430 it is given. Use this. This is for the main engine. So it is 9.81 into 4 into 430. I am getting here 4218. So this is what effective exhaust velocity, 4218 meter per second. And for booster, for booster P230, it is G into ISP 981 into ISP, I think 275 is given, 275, right? 27. If you go (9.81 into 275), this is 2697.75. I can write 2698. I can write round off meter per second. These are the effective exhaust velocity, right? Now we are going for second, exhaust mass flow rate. So second point, what is the second point? 2, exhaust mass flow rate. What is the mass flow rate formula? M divided by thrust divided by V effective. Yes, this is the formula. Thrust divided by V effective for main engine. All formula M, how this come? M dot T upon V effective. Already I have derived in the sense explained for the multi-staging, parallel multi-staging. So this formula already known. You just go and see back now. So for main engine, what is the M dot, which is the mass flow rate of main engine? Thrust they have given to us. Check what is the value of thrust they have given for the main engine. It is 1,114 divided by, what is the effective exhaust velocity for the main engine? 4218. So this is nothing but kilonewton, not 1,114 divided by 4218, and it is in kilo, so multiply by 1000. Thrust is given in kilonewton, so it is 264.1 I am getting. Similarly for booster P230, but in this case if you check the mass flow rate of booster, this value will be what? It is nothing but thrust. What is the thrust they have given to us? It is 6470 divided by mass flow rate you have calculated, that velocity 2698. So 6470 divided by 2698, 2.39, just multiply by 1000, 2398. See kg per second, so much amount you can see. That's the reason once it is lift off, you might have seen that exhaust amount. It is so much. Why? Because 2398 kg per second you are getting mass flow rate, exact mass flow rate. So for that reason, you have seen, might be you have seen when the rocket is what lift off during the operation. So much exhaust gases you may get. That amount is what so huge. You can check that mass flow rate, that amount 2398 kg per second. You cannot believe, see that amount, how much it is, but it is there. What you can do? Now we are going for the next, which is called average effective exhaust velocity. So this formula already I have given. So each and every formula I have given. So I am not going to write again that like what is the source of the formula, because already it is given for the parallel staging rocket. You check previous, go back and check, then you will get that. So third is nothing but average effective exhaust velocity. Average effective exhaust velocity. How to get this average? So that time I had written formula. It is the total thrust divided by total mass flow rate, m dot total. This formula I had given. So what is the total thrust? If you check, now we have first will be for the main engine plus thrust for the booster. And how many booster we have? 2 booster we have. So this is the total thrust divided by total mass flow rate, and mass flow rate of the main engine plus 2 into 2 booster we have mass flow rate of the booster. Whatever amount you have calculated, it is for single one. Okay. So what calculation you have done here, like for main engine and for booster? So this is for each. Okay, that value you have calculated, right? Now if you go for the effective exhaust velocity for the average value, so you need to write this. What is the main thrust amount? 111, what I remember, 1114 plus 2 times into, check that thrust for the booster you had calculated, it was 6470. Here it is given 6470, and mass flow rate for the main, you just know, you have calculated, it is 264 plus 2 times of the booster, 2398. You need to find this value. So this will be what? Effective exhaust velocity average value. So this value you are getting here, 2777 meter per second. No? So this value was required. And remember, whatever the amount of thrust, it is in kilonewton everywhere. 1114 6470. If you say, I will take this and write 10 to the power 3, there should not be any confusion, because clearly in thrust formula here they have mentioned this is also 10 to the power 3. Okay, because kilonewton they have given, so there should not be any confusion. In my calculator I am multiplying by 1000, and that time here also, see, it is given in kilonewton, this value. So this is kilonewton. Okay, so there should not be any confusion. All right, now the next value will be I think average exhaust velocity you have done, average effective exhaust velocity. Now average specific impulse will go last one. Okay, so average specific impulse, this is point number 4. So I would say here this problem was both series multistaging and parallel multistaging. It was so easy, and question is very important most based on this multistaging. average specific impulse. Okay, how to get this? Simple. Go to the basic formula only. That ISP, we know ISP is what, if you go back and previous to previous lecture, I had derived this formula, V effective divided by G. This is the formula, general formula. If I say what is the ISP average, so simple, what is the effective exhaust velocity you have calculated, you just write average divided by G. Simple one only. What is the average velocity? 2777, 2777.47 divided by 9.8. If you do this, then you get, so divided by 9.8, it is approximate 283.41 second. Done. So this was the problem based on multi-staging, and it was simple. At the same time, each and every steps I have explained. So I believe that